السلام عليكم. هنبدأ إن شاء الله الجزء الرابع من الريفيجن بتاعنا، وزي ما قلت لكم هبدأ لكم بجزء الأورجانيك لأن ده أكتر جزء مطلوب وأكتر جزء إن شاء الله هيكون موجود في الامتحان. Let's start with introduction to organic chemistry. Hydrocarbons. What's meant by hydrocarbons? Hydrocarbons is considered as the simplest organic compounds and molecules that contain carbon and hydrogen only. Remember that only contain one mark in this part. The word only is important here. Virtually all organic compounds contain carbon and hydrogen, but hydrocarbons contain only carbon and hydrogen. Organic compounds can be described as saturated, which containing single bonds only, and unsaturated, which contain double or triple bond, which will be discussed later. As you can see, in this example of organic compounds, propene, ethanol, butane, ethanoic acids, organic compounds which contain lots of compounds. When we talk about types of formula for organic molecules, first one is empirical formula, and we talked about this before. An empirical formula tells you the simplest whole number ratio of atoms in a compound. It can be calculated from experimental data as we just calculated in more chapter. Also sometimes empirical formula considered as the same as molecular formula. We did this in topic 1E, moles. For example, empirical formula of methane CH4, it's considered as the same as molecular formula. However, empirical formula for ethane is CH3, whereas molecular formula is C2H6. When we talk about molecular formula, a molecular formula counts the actual number of each type of atom present in a molecule. For example, molecular formula of butane C4H10 and the molecular formula of ethene C2H4. The molecular formula is considered as multiple of empirical formula. For example, if empirical formula is CH2, so molecular formula may be C2H4, C3H6, C4H8, and so on. The ratio of C to H must be always the same as empirical formula. Also, molecular formula tells you nothing about the structure, how atoms join together. Molecular formula used very rarely in organic chemistry, but they do not give any useful information about the bonding in the molecule. You might use them in equation for combustion, for example, for simple hydrocarbons, when the structure of molecule does not matter. It's like combustion of butane, for example, in presence of oxygen to give carbon dioxide and water. In almost all other cases, you use structural or displayed formulae. When we talk about general formulae for many different families of organic compounds, which known as homologous series. Example of homologous series: alkenes, alcohols, carboxylic acids, and esters. If you check general formulae right here, check this one. For alkene, whatever, CH4, C2H6, C3H8, C4H10, coming from the same general formula, CnH2n plus 2. For alkene, CnH2n. For alcohol, CnH2n plus 2, then O. So when we talk about general formulae, we talk about homologous series. Homologous series will be discussed in more details later, but homologous series is a series of compounds with similar chemical properties because they have the same function group, but each member differs from the next by one CH2. Members of homologous series can be represented using a general formula. The general formula for alkenes, as I told you, CnH2n plus 2. For methane CH4, 1 carbon atom, and 2 multiplied 1 plus 2 equal 4 hydrogen atoms. For propane C3H8, 3 carbons, and 2 multiplied 3 plus 2 equal 8 hydrogens. We can work out dodecan. Dodecan is 12 carbon atoms, So number of hydrogen will be 26. 12 times 2 equal 24 plus 2 equal 26. Different homologous series usually have different general formulae. For example, alkene CnH2n, as I told you, and alkyl CnH2n plus 2O. A functional group of an atom, a functional group of a compound is an atom or group of atoms that determine chemical properties of the compound. Let's check this. For example, functional group of alcohol containing OH, functional group of alkene containing C double bonds here. All compounds in the same homologous series have same functional group. For example, functional group of alcohols OH and functional group of alkene C double bond C, as I told you. When we talk about structural formulae shows how the atoms in molecule are joined together. Two ways of representing structural formulae. They can be drawn as a separate formula for structural formula, or they can be written in condensed structural or condensed form by just omitting all carbon-carbon single bonds and carbon-hydrogen single bonds and write it like this: CH3, CH2, CH3. When we talk about disparate formulae show all bonds in molecule or individual bonds between carbon and hydrogen, or bonds like this. As you can see, the structure of whatever butane like this, you can see all bonds between carbons and hydrogens. So all bonds must be shown as individual lines in molecule. You need to remember that each line represents a pair of shared electrons in covalent bond. Note that it's important to remember that carbon always form 4 bonds, hydrogen form 1 bond, oxygen will form 2 bonds, halogen like chlorine or bromine just 1 bond. How to draw structural formula? For anything other than the smallest molecules, drawing a fully disparate formula is very time consuming. To simplify this, you can use CH3, CH2, showing all carbon and hydrogen bonds as you can see. For butane, CH3, CH2, CH2, CH3, as you can see. Both of this exactly the same. Molecular formula C4H10, but molecular formula does not give you the same information. You can draw it like this, all of this the same because the chain is continuous. It's like the structures here. Rotation about single bond is free, so each structure show 4 carbon atoms joined together and the chain has simply twisted. This is happen in real because atoms can rotate around single carbon-carbon bonds as shown in figures. A molecule of propene, for example C3H6, has carbon-carbon double bond. This is shown by drawing 2 lines between carbon like this, 2 pairs of shared electrons, and simplified structural formula as you can see. When we talk about the disparate formula of propene, it's like this as you can see. And let's start naming organic compounds. We use code letter for number of carbon, mass, S, prop, biot, bent, hex. For example, butane is 4 carbon atoms, propane, chain of 3 carbon atoms. When we talk about alkanes are considered as homologous series of similar hydrocarbons, which considered as compounds of carbon and hydrogen only, or the carbons are joined to each other with a single covalent bond. Compound like this coded with ene at the end, so ethene, 2 carbon atoms with all single bonds. When we talk about alkenes are homologous series of hydrocarbons contain carbon-carbon double bond. For example, ene, CH2 double bond CH2. With longer chains, the position of double bond vary in a chain. As you can see, if we talk about biot, so we have to mention biot 1 ene double bond in carbon number 1 or biot 2 ene double bond in carbon number 2. How do you know which end of the chain to number from? You must give or start numbering from the end which produces the smaller number in the name. 1 is preferred in this case. Whatever here or here is the same, beyond 1 in. You have to start from the side that gives the double bond lowest possible number. If you have branches like methyl or ethyl, just mention the position of branch. It's like 1, 2, so 2 methyl butene. So name the molecule, choose the longest possible continuous chain, then position of side chain is shown by numbering the carbon atoms from the end of the longest chain that produce the smaller number in the name. The longest chain in molecular figure like this, it's 4 carbon atoms, so biot, no double bond, so butene, and methyl in carbon number 2, so it's named as 2-methyl butene. If there is more than one side chain, you have to describe position of each of them. Choose the longest possible continuous chain, and you can write 2, 2 dimethyl propene. This means 2 methyl groups attached to carbon number 2. If he asks you to draw structural formula of 2,3-dimethyl biot 2-ene, you can draw it 1, 2, 3, 4 carbon for biot, double bond in carbon number 2, and 2 and 3 dimethyl. Just complete hydrogens. Carbon number 4 needs 3 hydrogens to complete the 4 bonds. Carbon number 3 complete all 4 bonds. Also carbon number 2 make all 4 bonds. First carbon need 3 hydrogens, so it will be CH3. Let's start talking about structural isomerism. Structural isomers, molecules with the same molecular formula but different structural formulae. It's like structural isomerism in alkanes, for example C5H12. You can draw it in 3 different forms. You can draw it all carbons of the same chain continuous in one straight chain, or you can do it branched like 4 carbons with 1 branch like 2-methyl butene, or you can draw it as 2,2-dimethyl propane. If you look carefully at the structures in the figure above, you will find that we break one of the bond and add the branch on middle carbon, not terminal carbon. Reconnect them and change between them. Then we remove another one and put it in the middle carbon. So a straight chain isomer is called pentane. This one is called 2-methyl butane, and this one will be 2,2-dimethyl propane, as you can see. Don't be confused with this one. This one also 1, 2, 3, 4. It's considered as 2-methyl butane, but rotated. When we talk about structural isomerism in alkenes, like ethene and propene, no structural isomerism, only one structure present. Starting from 4 carbons, it's like biot 1-ene and biot 2-ene, position of double bond will be changed, or you can draw it as 1, 2, 3, so it's called propene with 2-methyl in carbon number 2. We can branch them, or also we can change the position of the double bond. When we talk about alcohols, in alcohols it's considered as homologous series with OH functional group and end with ol, methanol, ethanol, propane 1-ol because the OH in carbon number 1, or propane 2-ol because the OH in carbon number 2. The names all end with ol because OH is considered as the functional group, number of carbon indicated by mess, s, prop, and so on. We have 2 different isomers of propane 1-ol and 2-ol, propanol. So propane 1-ol and 2-ol, as I told you, considered as isomers because bond would have to be broken to get one from the other, just changing the position of OH from carbon number 1 to carbon number 2. Some chemical reactions of organic compounds, we have to classify some reactions of organic compounds, and this reaction will be discussed in detail in the next few chapters. First one is combustion, burning. All organic compounds can undergo combustion reaction. Combustion reaction is burning and involve reaction with oxygen. Combustion of hydrocarbon in excess of oxygen gives carbon dioxide and water with a large amount of heat energy. We use it for heating, we use it for camping stoves outdoors. Similar reaction can occur in case of alcohols, but take care in balancing that oxygen of alcohol must be included. 2 multiply 2 equal 4 oxygen, with 3 multiply 1 equals 3, 3 plus 4 equals 7, 3 multiply 2 equals 6, plus 1 oxygen present in alcohol. When we talk about substitution reaction occurs when atom or group of atom is replaced by different atom or group of atom. In this case, we replace one hydrogen, this one, with bromide, halogen atom. Addition reaction involve adding something is added to a molecule without taking anything away. Just breaking one of the double bond and adding 2Br to give 1,2-dibromoethane. Let's start talking about crude oil. Crude oil is finite, non-renewable. Once all the existing supplies have been used, they will not be replaced, or at least not for many million years. Crude oil is this black sticky liquid which is essential for modern life. When we talk about crude oil, it contains hydrocarbon, mixture of hydrocarbons, which we define at the beginning of this session as compounds contain carbon and hydrogen only. How the physical properties of hydrocarbons change with molecular size. As you increase number of carbon atom and hydrocarbon molecules, physical properties of compound change. Most of these changes result from increasing attraction between neighboring molecules. As molecules become bigger, the intermolecular forces of attraction become stronger and become more difficult to pull one molecule away from its neighbors. As the molecule becomes bigger, the following changes occur. Boiling point increases. The larger the molecule, the higher the boiling point. Also, because of large molecules are attracted to each other more strongly than smaller ones, more energy is needed to break these stronger intermolecular forces of attraction. Also, the liquid become less volatile. The bigger the hydrocarbon, the more slowly it evaporates at room temperature, because bigger molecules are more strongly attracted to their neighbors. So, do not turn into gas so easily. Also, the liquid become more viscous and flow less easily as you increase number of carbons. Liquid containing small hydrocarbon molecules are runny. Containing large molecules flow less easily because of the stronger force of attraction between their molecules. The liquids become darker in color, and bigger hydrocarbons do not burn as easily as smaller ones. This limits the use of bigger ones as fuels. Separating crude oil. Crude oil itself has no uses. It must be separated into fractions before it can be used. The fractions are mixtures but contain narrow range of sizes of hydrocarbons with similar boiling points. We use fractional distillation to separate crude oil into fractions. This is carried out in an oil refinery. When we talk about fractional distillation, crude oil is heated until it boils, and the vapors pass heated from here, and the vapor pass in fractionating into fractionating column, cooler at the top and hotter at the bottom, and the vapor rises up the column. How far up the column a particular hydrocarbon moves depends on its boiling point. Suppose that hydrocarbon boils at 120 degrees Celsius. At the bottom of the column, the temperature is much higher than 120, so the hydrocarbon remains as gas. As it travels up the column, the temperature of column becomes lower. When the temperature falls to 120, that hydrocarbon will turn into liquid. It condenses and can be removed. So smaller molecules have lower boiling point and gets further up the column before they condense, while longer chain hydrocarbons have higher boiling point and condense lower down in the column. This way, the crude oil is spread into different fractions, various fractions. The hydrocarbon and refinery gas fraction, the figure above, have very small masses and their boiling point so low, so temperature of the column never falls low enough for them to condense to liquid, still as gases. The temperature of column is not hot enough to boil some of very large hydrocarbons found in crude oil, so it remains as liquid and removed as residue from the bottom of the column, like bitumen used in road making. Uses of the fractions. Use it as fuel. Hydrocarbons burn in oxygen to form carbon dioxide and water and release a lot of heat energy in this process. Various fractions can be used as fuels. Fuel is considered as substance which, when burned, release heat energy. For example, burning methane, which is considered as major constituent of natural gas, gives carbon dioxide and water. Burning octane, which is petrol or gasoline, gives also carbon dioxide and water. If there is not enough air, oxygen is not enough, so incomplete combustion will occur, and this leads to formation of carbon, soot, black, or carbon monoxide instead of carbon dioxide. If methane burns in badly maintained gas appliance, there may not enough oxygen available, so it will give carbon monoxide. Carbon monoxide is toxic. Formation of carbon monoxide from incomplete combustion is very dangerous because it's colorless, odorless, and very poisonous. Carbon monoxide is poisonous because it reduces ability of blood to carry oxygen around the body. This will make you ill, or may even die. Not enough oxygen gets to the cell in your body for respiration to provide energy. Note that carbon monoxide combines with hemoglobin molecule which carries oxygen in red blood cells. Preventing it from carrying oxygen, it binds more strongly to hemoglobin than oxygen itself. When we talk about refinery gases is mixture of whatever methane, ethane, propane, butane can be separated to individual gases if required, but commonly used as liquefied petroleum gas for domestic heating and cooking. When we talk about gasoline is petrol, mixture of hydrocarbon with similar boiling point and used as fuel in cars. Kerosene is used as fuel for jet aircraft and as domestic heating oil, such as paraffin for small heaters and lamps. So we use kerosene for jet aircrafts. When we talk about diesel, it's used for fuel for buses, lorries, and some cars and some railway engines. Some is converted into more useful organic chemicals, including petrol, by process called the cracking. We'll talk about it. That's for diesel. For fuel oil, it's used for ships and also for industrial heating, For bitumen, it's thick black material which is melted and mixed with small pieces of rocks to make top surface of roots. What is the environmental problems associated with burning fossil fuel from crude oil? Fossil fuels include coal, gas, and fuels coming from crude oil. The major environmental problems is associated with burning fossil fuel that carbon dioxide produced when hydrocarbons are burned. It's considered as greenhouse gas, trap the heat radiated from Earth's surface, originally from the sun, and lead to climate change. But the main problem is acid rain. Sulfur dioxide and oxides of nitrogen can cause acid rain. Rain is naturally slightly acidic because of dissolved carbon dioxide, but acid rain with pH lower than 5.6 due to presence of pollutants. The pH of acid rain about 4. Acid rain formed when water and oxygen in the atmosphere react with sulfur dioxide to form or produce sulfuric acid, and with oxides of nitrogen to produce nitric acid. Sulfur dioxide and oxides of nitrogen come mainly from power stations and factories burning fossil fuels and from motor vehicles. Fossil fuels contain a small amount of sulfur. Sulfur is burnt. Sulfur reacts with oxygen to form sulfur dioxide. Then sulfur dioxide reacts with more oxygen and water to give sulfuric acid, which is responsible for acid rain. Remember that sulfur dioxide reacts with water to give also sulfurous acid, another acid but weaker. Petrol engines. In petrol engines, spark that used to ignite petrol air mixture to power the car. The temperature reached in engine is high enough to allow nitrogen and oxygen from air to combine, produce oxides of nitrogen, NO. These nitrogen oxides can be converted into nitric acid, which contribute acid rain. Acid rain is major problem because it has destroying effect on trees, live on lakes. Acid rain also kill trees, fishes, and if lake water is so acidic, it will not support life at all. Also limestone building and marble statues, which made of calcium carbonate, affected with acid rain, and also iron can be attacked by acid rain. Calcium carbonate, when react with acid, it gives calcium sulfate, water, and carbon dioxide. And the solution for acid rain, removing sulfur from fuel. This is done before burning petrol in car, and refine the gases from power station and factories. Removing SO2 and nitrogen oxides occurs also by catalytic converters in cars. Let's start talking about cracking. Although most of the fractions from fractional distillation of crude oil are useful as fuel, but some fractions are more useful and more profitable to sell than others. The amount of each fraction obtained depends on proportions of various hydrocarbons in the original crude oil, not the amount in which they are needed. So the problem is too far many long-chain hydrocarbons which are not in such high demand, we don't need this, and not as profitable to sell. Also, there are not enough short-chain hydrocarbons that can be used as fuel for cars. So, far more petrol is needed than can be supplied by just separating crude oil into fractions, so we can do cracking. Cracking is a process in which long-chain alkanes are converted to alkenes and shorter-chain alkenes. The big hydrocarbon molecule in fuel oil, for example, can be broken down into smaller ones needed for petrol. It's like C14H30 gives C10H22 plus C4H8. How catalytic cracking works. The fuel oil fraction is heated to give a gas and then passed over a catalyst, whatever, silicon dioxide, which is called silica, or aluminium dioxide, which is called alumina, at temperature 600 to 700 degrees Celsius. They may ask you about this. Cracking can also be carried out at higher temperature without catalyst, which is called thermal cracking. Cracking is just an example of thermal decomposition, a big molecule splitting into smaller ones on heating. Most of the hydrocarbons found in the crude oil have single bonds between carbon atoms during cracking process. Single bonds are broken and new double bonds are formed. So molecule broken in random way, check this one. This large molecule broken in random way and form double bonds like this. So as you can see, C13H28 gives C2H4, C3H6 and C8H18, which is considered all of them useful, ethene, propene and octane. This cracking gives two types of useful molecules for chemical industry, ethene and propene, used to make polymers, plastic, which were discussed later, while C8H18 is used in gasoline, component of gasoline. Two important reasons why oil companies carry out cracking: to produce more petrol and to produce more alkene, which used in formation of plastics or polymers. Alkenes are more reactive than alkanes and have other uses. The molecule have spread quite differently, as you can see. All of this will be useful. For all of them, it gives alkene, and also it may give hydrogen in some breaking. So this mixture will have to go through a lot of further processing, including fractional distillation, to separate everything into pure compounds. Let's start talking about alkanes. Alkanes are the simplest family of hydrocarbons. Hydrocarbons, as we mentioned several times, contain carbon and hydrogen only. Many of the alkanes used as fuels. Methane is considered as major component of natural gas. Ethane and propane also, we mentioned, used in liquefied petroleum gases. The first 5 members of alkane series, as you can see, the alkane described as saturated hydrocarbon because it contains only carbon-carbon single bond and no double bond. Remember, if he asks you to describe or write about saturated hydrocarbon, you have to mention it worth 3 marks. You have to mention contain only single bond, and also you have to mention the definition of hydrocarbon as well. Isomers of alkanes. Isomers are compounds that have the same molecular formula but different structural formulae. Alkanes in the table considered as a straight chain, unbranched, but isomers of whatever bentane, we can draw it as this one, 2-methyl bentane, and whatever 2,2-dimethyl propane, and the bentane itself as a straight chain, and this one is considered as isomer for butane. When we talk about homologous series of alkanes, homologous series contain same functional group, similar chemical properties, trend or gradation in physical properties, and same general formula, and differ from each other by CH2 unit. The alkane is considered as the simplest homologous series, and alkane do not really have functional group because it just contains carbon-carbon single bond and carbon-hydrogen bonds. When they ask you about homologous series in exam, only write about properties, second and third, which is a same functional group, similar chemical properties, considered as 1 mark. They have similar chemical properties because they have the same functional group. When we talk about members of homologous series, they have the same general formula. It's like CnH2n plus 2 For propane, for example, C3H8 and each one differ from the previous one by CH2. Members of homologous series show trend or gradation in physical properties, as you can see right here. Boiling point increase by increasing the number of carbon atoms, as you can see here. So the first 4 alkanes are gases at room temperature. All other alkanes you will meet in this service are liquid. They start from carbon 18. And members of homologous series, when increase in size, boiling point also increase. Molecules become bigger. The strength of intermolecular forces of attraction between them increase. So more energy required to break the attraction between molecules and its neighbor. Members of homologous series have similar properties. Chemical properties depend on functional group and the bonding within the molecule. Alkanes contain only single bond between carbon and single bond with hydrogen, so they behave in the same way. Also, they contain strong bond, so unreactive organic molecules, quite inert. They just do 2 reactions, combustion, burning, and we talk about combustion. If enough oxygen, they burn completely to form carbon dioxide and water. If there is not enough oxygen, they make incomplete combustion to form carbon monoxide or even soot, and we talked about this before. In combustion reaction, it's highly unlikely that hydrogen will always give water. Hydrogen is considered as very flammable, so always obtain water, even if insufficient oxygen. The other reaction of alkane is substitution. Alkane react with hydrogen in presence of ultraviolet light, sunlight, to form halogenoalkane like this. Just replace one hydrogen with one halogen. So hydrogen atom of alkane replaced by a halogen atom. This is called substitution reaction because one atom has been replaced or substituted by different one. Mixture of methane and bromine gas is orange because presence of bromine. When exposed to sunlight, it loses its color. Mixture of bromoethane and hydrogen bromide gases are formed. Similar reaction can occur in presence of ethane with chlorine in UV light, as you can see right here, just removing one hydrogen and adding one chlor instead of it. We have to know mono substitution, only one hydrogen replaced in each case. When propane reacts with bromine, 2 possible products structure isomer to each other, 1 bromo and 2 bromo propane. Product from this substitution of alkane, called halogenoalkane, when bromine reacts with propane, it gives 1 bromo and 2 bromo propane. Last part, when we talk about alkenes are homologous series of hydrocarbons, contain carbon-carbon double bond. It's considered as functional group of alkenes, as you can see right here. It's not possible to have alkene with 1 carbon because alkene must contain carbon-carbon double bond. So first alkene containing 2 carbons. When we talk about isomers, for alkene, we can change the position of double bond PO1-ene and PO2-ene. Also, we can write 1 branched chain isomer, as you can see right here. It's considered as unsaturated hydrocarbons because it contains double bond, while saturated compounds contain only single bond. General formula of alkene CnH2n and number of hydrogen is considered as twice as number of carbon atoms. This means all alkenes have same empirical formula, which is CH2. Physical properties of alkene very similar to alkane. Small alkene up to 4 carbon atom gases at room temperature, starting from C5 until whatever next 12 considered as liquid, who show trend in physical properties. Also, they can do combustion in air, but alkenes are much too useful to waste by burning them. They react by addition. C double bond C is considered as functional group. This functional group determine chemical properties of compound. So alkenes have characteristic chemical properties differ from alkenes. Alkenes more reactive than alkenes also undergo addition reaction. Part of the double bond break, become single bond, and electron used to join other two atoms to each carbon gain one atom. Addition of bromine add to alkene without the need of heat, right, or even catalyst, just breaking one of the double bond and adding two bromo, one in each carbon. The color of bromine is orange. Once it reacts, it converted to colorless, so this reaction is considered as test for unsaturation. Any compound containing carbon-carbon double bond will react with bromine in similar way to give carbon-carbon single bond, not double, and add to bromine, and the color of bromine change from orange to colorless. This is considered as familiar question in exam. So bromine water completely decolorized in presence of carbon-carbon double bond, while alkenes do not decolorize bromine water because they do not contain carbon-carbon double bond. Addition reaction of bromine and propene is very similar to ethene. One of the carbon-carbon double bond breaks and two bromine add across the double bond. It gives 1,2-dibromo-propane. 1,2 mean carbon 1 and 2. Dibromo contain two bromine atoms in the first and second carbon of propane. Hydration is considered as related to unit 2, but just adding one hydrogen and one OH for ethene, for example, it reacts with steam, water vapor, in temperature 300 degrees Celsius and the pressure 60 to 70 atmospheric pressure, and the catalyst used is phosphoric acid, and this reaction produce high purity ethanol in industry. خلينا نقول ان احنا كده الحمد لله خلصنا جزء الاورجانيك، واعتقد مش هيبقى فيه وقت ان احنا نعمل حاجة تانية اضافية. معلش اعذروني ان احنا ما عملناش الباقي، بس يمكن عشان الوقت ضيق وانت اكيد خلاص هتبقى عايز تنام عشان الامتحان بتاعك مش هينفع تسهر، وانا بصراحة مش قادر اعمل اكتر من كده. اتمنى ان انتوا ما تزعلوش مني، واتمنى ان انتوا تكونوا استفدتوا بالريفيجن دي. اتمنى تدعوا لي دعوة حلوة. الريفيجن دي بتمثل تقريبا كده اكتر من نص الامتحان، بالذات جزء الاورجانيك، فعشان كده يعني ما تنسونيش بدعوة حلوة وانتوا بتمتحنوا بكرة لو عرفتوا تجاوبوا حاجة بسبب المراجعة. ان شاء الله تعرفوا تجاوبوا الامتحان كله، بس اللي اقصده لو افتكرت حاجة من اللي انا قلتها لك وجاوبتها كده وافتكرتني، ادعيلي دعوة حلوة اثناء الامتحان. اشوفكم على خير ان شاء الله، بالتوفيق، وهستنى تطمنوني، وما تنسونيش بدعوة حلوة. سلام عليكم.